Hello, everybody. The topic is GeoGebra reasoning tools for humans and for automatons. We will present two tools, basically based on GeoGebra for humans, and we call them GeoGebra Discovery toolset. It will include the relation command and tool, the locus equation command and tool, the prove and prove details commands in GeoGebra. This is for humans. For automatons, we introduce two tools or commands, the discover command, and there will be something that is a bit of outside of GeoGebra, namely the automated geometer. Then we will conclude some reflections on the pros and cons. So some motivating preliminary history. This professor here is Wenxin Wu from China, and 3 years ago he passed away, but he gave a fantastic lecture, as far as I know, in 1995 about his research topic, and it was proving mechanically by using algebraic geometry, and this was very, very fast and efficient at the time. So it was a revolutionary idea. And he emphasized that geometry problem solving is more important than proving itself. So this was one idea from Professor Wu 25 years ago, that even if we are talking about mathematics and proving, problem solving is the main point. And on the other hand, algebra and geometry should be kept in pace in the teaching. So both of them are very important. Let me refer to the original paper. It was published in the proceedings of the first ATCM in 1995. Then another very important example, hopefully also very motivating. It was last year. These professors, Zhang, Zhong, Jia, and Liu, were talking about a very similar topic. In fact, they mentioned not just Tarski and Wu and Zhang, who were pioneers and made profound progress, but they point to Gröbner basis. Gröbner was a European mathematician, and he introduced many new concepts in algebra. And his student, Bruno Buchberger, he was a kind of pioneer of finding a new method that is a good algorithm to manipulate on algebraic equations, equation systems, and to develop a mathematics robot for automated solving of elementary mathematics problems. So this was the topic from these 4 professors last year in China. This is based somehow on the same idea we are working on. Almost 25 years of difference, but of these 2 ATCM talks. But we need to emphasize that what they did, it was a kind of a direct ancestor of origins of our tools based on algebraic geometry. And they had very, very similar goals, namely to solve things in elementary geometry, difficult or not very difficult problems, but actually to solve problems. And to emphasize again, Wu had this point, not proving, but solving. So this is emphasized. Okay, let's go into the detail, some introductory examples on the geometer automaton, and maybe most of you know that automaton is a Greek word, a mechanism that is relatively self-operating. Its plurals are either automatons or automata, very well-known words. If we add the other word geometer, so geometer automaton, it's a mechanism that successfully performs in a self-operating mode the tasks that human geometers are expected to accomplish, to conjecture, to prove, to refute, or even discover geometric properties. So maybe a short summary what we did, and we distinguish between two things. Basically, the one thing is here in this square, we built a system inside GeoGebra with several tools. Um, you can click on these icons and you can use these tools. Or in the background, there are some low-level comments that are not so typically used by normal users, but power users can make a benefit of using them. We mentioned GeoGebra, so these are inside GeoGebra, and of course there was a big uh, collaboration between the primary developers of GeoGebra, mainly by Professor Hohenwarter and his great team to uh, to have an effective implementation of these ideas inside GeoGebra. On the other hand, there is a web application that is not closely related to GeoGebra, but GeoGebra's API in a web browser is heavily used for this program. So these are the two sides of the same coin, but the aim is that user, student, teacher, researcher can have a benefit of automated reasoning. So uh, we can also make a difference between these two kind of tools, and I colored the tools that are useful for humans by using this green or bluish color. So relation, LocusEquation, these two tools, and the level comments, proof details, they are for humans mostly, and the rest, Discover and the web application, is kind of very automatic uh, thing, because for that we can obtain a lot of new, um, not very new, but a lot of different properties of a geometric figure. So let's start with the relation tool. Relation tool is actually there in GeoGebra for many years. It was in the first version of GeoGebra there, so maybe 2002 or even 2001, but it was purely numerical. So nothing symbolic, nothing algebraic was introduced at that time. Um, well, I would like to uh, illustrate this concept by using a very, very old task or problem from 1986. So there was a conference in Kuwait, and this nice task, this nice question was raised by um, Hausen and Wilson. They um, summarized the topics of the conference, and well, it was quite easy and simple. There's a square. We draw two segments. These are the midpoints of these two sides. And the question is, if we consider the intersection points with the diagonal, what kind of equality can be obtained here? So we can do the same with GeoGebra automated reasoning or just reasoning tools. Let's see what happens if we do it in GeoGebra. Um, Well, I will open the software now, and okay, so this is it. We will distinguish between two versions. The one version is here, GeoGebra Classic 5, and GeoGebra Discovery that contains some extra improvements. It's built on the top on GeoGebra Classic 5. And in the background, you can see also a web page that is GeoGebra Classic 6, and it is also kind of extension of GeoGebra in the direction of a web application. So let's see how it is created. I will open a file now, namely this one. And it was constructed in this GeoGebra Discovery. And you can see that after construction, M, N, and P, these three segments, look like to be the same. Well, rounding was set to 15 decimal places. So if you doubt that they are the same, of the same length, well, you can be more or less, yes, you are right. You are right. It's still a question. So we can drag the points, and you can see that sometimes the difference, the numerical difference is, well, a bit more different. So that's why we need, or we may need, kind of exact answer, symbolic answer in the background. And by using the relation tool, I click on the relation tool and select two segments, for example, M and N. And in fact, the answer by the relation tool is more or less well known. From 2002, it's there, but the new improvement that you can ask for something more in this new GeoGebra Classic 5 version. So let's click on it, and GeoGebra Discovery will deliver the answer. Yes, they are equal, M and N are equal. Actually, there can be some so-called non-degeneracy condition. It's safer to put A and B to different positions. Otherwise, the construction could be degenerate, and the questions have no meaning anymore. So this is a kind of condition that is also produced by the symbolic computation. There are also a few other tools. So let's have a look on them. Basically, the first tool, low level tool, which is mentioned after the relation tool, is ProveDetails. ProveDetails means, well, we want to know something more about the proof, not just this nice report by the system, but we need something more. So let's see how it is working. So we enter ProveDetails and ask the question, is it true that M and N are the same? So the length of them, of course. And then we get the answer, yes, they are true under the condition A and B are not equal. So this is a kind of negation of the answer. So this is for power users who want to use GeoGebra as a command line system. And in fact, this is also available via the API. So if you want to use this from an external program, from a web page, by using JavaScript, for example, then this is very, very useful. And we will see some applications soon. Let's go back to the presentation, and you can see that there is another command, just prove, not prove details. And in this case, users can have kind of different output. So what happens if I use not prove details, just prove, then the answer is just true. This is a simple answer. Why? Because some users are not interested in the very detail. Yes or no? True or not? Actually, this is not so easy. It's a very complicated question because we translate the geometric problem into an algebraic problem, and then the answer will be translated back to geometry after computing the algebraic manipulations that can take many, many steps, um, sometimes millions of term uh, computations or manipulations are in the background. So it's completely different than using pure geometry in the background. But sometimes the algebraic manipulation cannot really decide if something is yes or no, true or false. We are somewhere in the middle, um, on the half of the input points. We have a yes answer. On the other half, we have a no answer. What to do in this case? So, okay, let's go one step further. The command locus equation can give you some more challenge. So sometimes we want to play a bit with the problem and not just enjoying the answer in a ready form. And that's why the command, uh, so this one is what I need. So this command is more interesting. So what are we doing here? We created a very similar construction, but this point E is not put on in the middle of AB, but we just put it somewhere on this side of the square. Well, we are interested uh, when it will be happen that the lengths n and p are equal to each other. So that's why we need the question locus equation n equals to p, and we want to know where to put point e in this problem setting. And then the system computes that if you put e in this position p, p is actually a kind of maybe I can show it here in a better fashion. So you can see it's a kind of circle, but this circle has a 0 radius. So this is just the point. If you put E in this point, in this position, then you will be able to get N and P. They have the same length. Of course, we can drag the figure point B, for example, and we can see that we always get kind of quadratic curve, actually a point in this case. We would like to emphasize that this program is not just for a laptop, for a desktop computer. You can do the same practically on all machines that have an internet connection, have a web browser. So, for example, my smartphone, it's a quite old one, 3 years old. It runs Android 9, and it is also capable of doing the same thing. So sketching up the figure, then clicking on the relation tool, then you can obtain the same result. If you want to download the software, you can go to the GitHub page or if you want to try the system, it's available on this link. So you can just try it. Well, a more difficult problem from the Chinese school. Chu was a student of Vincent Wu and wrote a book with 512 different geometry problems, and they were all solved by using an automatic system. So the same idea that was created by Wu, and we selected this example 230 from those more than 500 problems. Let's go into the detail. So we have a triangle, and we will step by step create first of all the circumcenter of the triangle. Of course, we need the perpendicular bisectors to do that. And then we create the midpoint of BC. Then we will mirror the point A about this midpoint BC. So let's do that. As a next step, we create the orthocenter of the triangle. It is the intersection point of the heights of the triangle. So this is the orthocenter, and this orthocenter will be also mirrored about a point, namely about A. So this is what we are doing. We mirror the orthocenter about the point A. Then we can learn, if we drag the points, that there is something which is always remaining property, and namely that the symmetric A, the circumcenter and the symmetric O, they look like they are collinear. So they are lying on the same line. And well, this is, of course, checked at the moment, not yet symbolically, but we can do the same with the relation tool is in the previous problem. So we can ask if the symmetric of A and this line that connects the circumcenter and the symmetric. So what can we conclude in this case? Well, first of all, a numerical check will be done, but then by using the more button, we will get not just that it is generally true that these 3 points are collinear, but also that we should be careful if A and B are equal, or the triangle ABC is non-degenerate, is degenerate, sorry, then we can have problems with this observation. So this is actually a complete theorem, complete geometrical theorem. What can we do? As a second step, we can do the same. So we can try the ProveDetails command. We want to prove yes, that this symmetric of A is an element. I need here some trick. Symmetric of A is an element of the line circumcenter symmetric of O. Yes, exactly. So this is how it works. Then I will get this low level result, but I can analyze this with a computer, for example. Experts can learn some detail closely. The same result can be obtained if we want to use just the proof command, not ProveDetails, but just the proof command. And in this case, we have an output of true. So if it's not interesting what are the non-degeneracy conditions. Okay, um, as a third step, we want to know, well, if we can conclude the same thing by using the LocusEquation command. Uh, of course, it's a bit more advanced, and we can do the same construction by using the same steps. But in this case, we don't use the point on the side BC, the midpoint, but a different point, so-called free point. So these completely free, we have the freedom to choose it. And then we go further and do this reflection about point D. So not about the midpoint. It could be the midpoint as well, but it's a kind of free point. So this is the symmetric of A. And then if we go further, we create the orthocenter again and mirror the orthocenter dot A. Then we can see that in this case, these 3 points, symmetric of O, the circumcenter is symmetric of A, so they are not really, they are not always, or not really, so they are not collinear. But we can actually ask the system to create this the answer. So this one, this is the command LocusEquation, and we can use the same Boolean expression here. So when is it true that the symmetric of A is a member of this line? Where to put point D? The answer is, please put D on this red line, then these 3 points will be collinear. So actually we have a bit of more result here. Now, so not just this midpoint of PC will do the job, do the result, but also some other points, and these points need to lie on this line. Well, it's a good question how we can construct this line. It's an open question, but we can challenge ourselves or challenge the others. Well, it's a good question. It is not answered by GeoGebra immediately, but there is some kind of suggestion or some hint in this output. The next slide is about the discover command, a kind of high-level possibility and a high-level way to obtain results from elementary geometry. This is already the output of the discover command when we try to learn some interesting facts on a square. So let's do it by using GeoGebra, the classic 6 version in a web browser, and I will switch this axis and the grid off. We don't need that. And how can we create this figure? So I will create a square by using a regular polygon, and I will just simply use this discover command, and I click on point A, wait 2 seconds, and then I can obtain this result here. So what is the result? GeoGebra Discovery found that there are 4 concyclic points, namely A, B, C, and D. There are 2 sets of parallel or perpendicular lines, namely AC and BD. They are perpendicular to each other, and the other 2 this CD and AB and AD and BC. So they are parallel and orthogonal to each other. And of course, there are some other information, namely AC equals to BD, and these four sides are equal to each other. Of course, you can say, well, some of these observations are trivial. Yes, that's true. So it's sometimes very difficult to filter out which piece of information is uh, simple, trivial, not interesting, or appealing. I think many of you know this nine point circle problem is, well, we have a few points in a triangle, not just ABC and the midpoints, but also the feet points and also the orthocenter and the midpoints between the orthocenter and the vertices of the triangle. So I think many of you know that this construction has a very interesting property, namely that these 9 points here usually are lying on the same circle. But we can do a discovery here again. So let's click on point D, for example, and let's collect some interesting information, piece of information on the figure. And yes, after some seconds, this 9-point circle is observed symbolically by the system, and some other information. Well, quite a lot of other pieces of information will be delivered by using the program. So this is how it works. And of course, if you want to observe just a couple of these properties, you can switch a couple of them off. So if you are not interested in these lines, then we can of course hide them and focus on the other results. We can obtain the same thing, actually not only in the discover command, but also in a web application. Web application will do practically the same, and the difference is that you don't have to install anything, and the focus can be not on just one point, one interesting point, but you can obtain information on the whole figure. So let's go back to the web browser, and I created here a tab for the automated geometer that is this is outside of GeoGebra. So it is not inside GeoGebra, it is outside, but it uses GeoGebra API as a low-level interface, and then the results will be presented to the user in a modern fashion. So let's click on the 9-point circle example here. So we load the same input figure, and we are interested actually in two things. So the equality of distances between 2 points and the consequently of 4 points. Then we select only these two properties to investigate, but the whole figure will be considered. And then we click on this start discovery thing, and in the background the system will start to find these symbolic properties. And after some seconds, so you can see that more than 5,000 properties will be considered combinatorially, and if property is found, then it will be printed here as a list. And well, we need to wait a couple of seconds, but of course this is so not very quick, because you have to manipulate on a big equation system. Equation system means sometimes 20 equations or even more. And theoretically, the number of steps is double exponential. Of course, we have a very, very good system in the background, a very good and effective computer algebra system, namely GeoGebra from France by Bernard Paris. And this is very well programmed and very quick to solve an equation system or manipulate on it. Well, we can see that there are 267 theorems, and I need to admit that some of them are just reformulations of previous knowledge, or we could somehow summarize the information or compress them. So actually the presentation is not the best, but in 1 minute we found several nice properties, and among them it's the circle. So we can see that the circle is there, and maybe some other properties can be surprising. I didn't know that there are so many circles in the background, for example, C, H, and while G and I, they are lying on the same circle. So it can be surprising in some sense. Okay, let's see some further examples. So this is the problem setting. Let ABC be an acute triangle. Suppose that points D and E lie on the side BC, such that D is between B and E and AD equals to CD. So these two are equals this one and this one. And the other hand, AE is equal to BE. So this one and this one. And we have also a point F that is put on a parallel line that is parallel to AB, and also on another parallel line that is parallel to AC. So this is the intersection of these two parallels, and we need to prove that FB, so this purple line and this other line is, so they are equal to each other. Let's go back to GeoGebra, and after we click on discover. So I would be interested if point F is interesting enough, we can learn yes. So these two segments are equal to each other. Some other information is also obtained that are not really interesting for us in this case because they are trivial in some sense. It's quite important that this problem is actually used for mathematics Olympiad, for running Olympiad, similarly to another one that was already among the non-selected problems for the International Mathematical Olympiad 3 years ago. So this is a shortlist problem. And in this case, if I do discovery again, let's click on O prime, then while after some seconds, we will be able to obtain this result that A, O prime, and F are indeed collinear. So this is indeed the median of the triangle. And on the other hand, we obtain some other interesting facts. For example, for me, it was not clear that this line here, HO prime, is parallel to the side BC, or well, this OF is perpendicular to it, so to them. So it could be interesting for the further steps when someone wants to prove this fact, this property. Good. Some further examples. If you have time and interest, you can go to our prover test database. We have here a test that is performed on more or less a daily basis. So we have a lot of examples, and the green results mean that in a certain version the result is okay. On the other hand, we also have a benchmark test for the LocusEquation envelope comments. Envelope is another comment that was not mentioned in this talk, but it's very close. And here, this is the main version that is important, and of 180 cases we have 178 working outputs. Sometimes the speed is not very fast, and this number is the degree of the polynomial that is obtained. Sometimes we have even something of degree 20. So it's quite complicated, but to have a working animation, it is still good. Finally, I'd like to talk about some didactical implications, but first, maybe the future of these GeoGebra reasoning tools. There are some improvements in the direction of making conjectures of geometric inequalities, and we use for that a Raspberry Pi version of Mathematica, and well, there are promising results. Also, there is an international collaboration of to create an intelligent geometry book led by Pedro Quaresma in Portugal, and we also would like to include, in some sense, readable proofs, but it's not so simple, not so easy, because the theory of algebraic geometry gives very little hope to do that. So we don't expect in the short term that we will be able to do that, but well, some results could be eventually done for experts to double check if the result is correct or not. So back to the didactics. After knowing that there is some future, hopefully, for these tools, we need to rethink the curriculum. So this is quite urgent, because even let's say 30 years ago, this was already a problem. Computers exist. We cannot forget this fact. We cannot ignore this fact. And so these examples show that computers can do a lot. Of course, we can think about the role of reasoning and proving, what opportunities, what differences involve using GeoGebra reasoning tools. And well, we can see that it can guide students to explore, to get hints, even if the question cannot be completely answered, just partially. It's very useful for thinking further, to try to solve problems. And of course, having a diagram to draw a locus, it's not just for the students, even for teachers sometimes. If we are thinking about math proofs, well, mathematics cannot live without proofs, but these proofs are indeed automatically obtained. So this is a very strange situation, and we need to think about, okay, maybe some parts of human thinking should be not just replaced, but to supported by mechanical computations. So it's quite surprising, and it requires something completely new and something completely new approach. Uh, Maybe you can think, well, geometry, if you are doing it like using a pocket calculator that can give a proof, it's not geometry any longer, but why not? So things are changing. And even in 1995, there was a revolutionary paper in the American Math Monthly, The Rise, Fall, and the Possible Transfiguration of Triangle Geometry by Davis, and he was quite clear that classical proof must move over. So this is the next step, and we should live with that. But it's not so bad because instead of focusing, proving, we can focus on problem solving. And this is what was supported by Vincent Wu 25 years ago in his ATCM talk. Yes, you're right. Mills grind slowly. The impact in education is very slow. We listed some literature from the last 60 years. So this was, it began with Galanter in 1959. Then there were many, many steps on this road. Maybe we can point you to a recent workshop presented in Brazil last year um, on the current achievements. While we try to collaborate together as an international community, but it's very, very difficult to convince not just politicians, but also colleagues that this is something useful. As a last web page, I downloaded something for you from the future. Not me, actually, but Doron Zellberger, the famous Israeli mathematician, and he practically wrote a book from the approach of Shalosh P. Eklund, his computer. The computer, it wrote this elementary textbook in 2050 approximately, and everything is automated, everything is computed by program. So this is not really new what we are doing, but we are just putting it in a new fashion, in a modern package. GeoGebra is available to millions of users, students, and teachers. It's free, and maybe this can speed up dissemination of these new ideas that are very close to us. Thank you very much for your kind attention. And if you want to read something more on the topic, maybe you can read one of these two papers. One is a chapter in a book, and the other one is an article in the International Journal of Mathematics, Education in Science and Technology, a quite recent one. So thank you again, and see you hopefully in person somewhere soon.